So good morning, good afternoon, good evening, depends on where you are today. So thank you very much to join us for another very interesting CASS talk. So today we have the pleasure to have here Professor Vasilis Pavlidis. But today we are here to listen to Professor Vasilis. And Professor Vasilis is an associate professor in the Electrical and Computer Engineering Department of Aristotle University of Thessaloniki in Greece and affiliated with the Department of Computer Science at the University of Manchester in UK. He holds the Master and PhD degree from the University of Rochester in New York and obtained in 2003 and 2008 respectively, all in electrical and computer engineering. From 2008 to 2012, he was a postdoc at the Integrated System Laboratory of EPFL in Lausanne, Switzerland. He has more than 10 years of research experience in the areas of on-chip interconnect modeling and design and emerging technology such as 3D integration and spintronics. He is the leading author of the book Three-Dimensional Integrated Circuit Design, first and second edition, and contributor to the software tool Manchester Thermal Analysis. He has delivered over 20 invited talks in academia, research centers, and industry, including a 5-day course at the University of Beijing, China. He is a senior member of IEEE and offers editorial service for several IC design and VLSI journals. So thank you very much, Professor Vasilis, to accept our invitation and to give this talk today in a very exciting subject. So the floor is with you to start your presentation.
Great. Good afternoon, everybody. Thank you once again, Ricardo, for the kind invitation. And I'm really excited to join this group of excellent speakers that you have gathered over the last couple of years, and you keep doing that. So today I'll talk about an issue that has been in the spotlight for several years now. And the reason I chose that is basically because we work on some new techniques relating to signal encoding as part of a couple of recent European projects. So all of this work that you will see today has been developed at the University of Manchester from one of my PhD students, Mrs. Eleni Maragoudaki, who defended her PhD earlier this week. So I'll start with basically a tutorial, since this is a CASS school, and then I'll present our results on some recent new techniques relating to signal encoding. But let me first rather answer, why do we need signal encoding, right? What's the need for this? So these couple of motivational slides, what they show is that over the years, we have performed quite well in improving the energy efficiency of computation. You can see here that we improved that about an order of magnitude over 5 years. But on the other hand, if you look at the graph at the right, the energy efficiency of the interconnects or communication, let's say between chips, does not improve so fast. So we have an improvement of about 2.5 times every 5 years. And below, where you can see is the breakdown of the energy required basically to execute an instruction, where this analysis has been done by the Mark Horowitz group, the professor in Stanford, where you can see that about 30% of the energy is required for communication, fetching effectively the instruction from the cache. So if you go and see some other works that have been investigated in other hardware platforms, like the one you see here, the Samsung Galaxy, the ARM Cortex-A9, all they seem to converge to the same conclusion, which is that when you execute different workloads, about 30% of the energy you utilize is basically for moving data around. So there is a headroom that we should and we can do something to reduce the energy of this energy component, basically, which will lead overall to lower power consumption. So as I foresaid, I'll spend some time, since this is a school effectively, to discuss techniques that have been developed over the past, I would say, 20 years. Of course, I'll give a glimpse of these techniques rather than going in detail. And then I will spend some time discussing the most recent techniques we have developed, which we call adaptive word reordering and serial tune transition encoding, and then we'll draw some conclusions. So when we talk about signal encoding, what we typically want to do is, if we start from this fundamental relation that describes the dynamic power component in a digital system, we want effectively to reduce the number of transitions that take place when we transfer information from, let's say, chip A to chip B, right? As you see at the bottom of this graph, we want to encode the data so that the number of transitions reduces. Therefore, this alpha coefficient at front of the power expression reduces, and overall your power goes down. Of course, at the same time, you need to be able to transfer all the information you desire, right? You can't just transmit a continuous 1 or 0. So I have basically split this introductory section to the techniques that are dedicated to parallel interfaces, and a few more that have been developed exclusively for serial interfaces. So let's try to cover first the ones that relate to parallel interfaces. And in all of them, in the vast majority of those, there is a fundamental assumption that the transmission of the data is source synchronous, meaning that you assume that the clock is available, is sent to the receiver chip, so that you don't need to recover the clock as well. Typically, this is not the case for serial communication, as we'll see later on, and that puts some additional constraints on the techniques you are trying to develop. But for the parallel links, this is the basic assumptions that the large number of techniques have basically followed, right? So to begin with, there are the static encoding schemes, and these are good as long as you know the characteristics of the data, all right? So this is critical. You analyze your application, you observe what is the different correlation of successive data, and then you can apply some smart encoding schemes, such as the gray code that you can see here, or tree-node code, and so on. And these seem to work well, for example, if you have addresses, memory addresses that are sequential, right? These two do not seem to work well if the addresses are not sequential, as you can see here. So in that case, there are other techniques like the beach solution or the probability-based matching that you see at the bottom of this slide, where again, they analyze the characteristics of the data that you desire to propagate. And again, I emphasize that you do that during design time, right? Not at runtime. And then you can apply some effective encoding scheme with some low overhead, circuit overhead. So this is good as long as you know what your application look like, right? But this is not always the case. So on the other hand, you have a longer list of schemes, if you like, or methods which are adaptive, and they do not require, because this is a rather strict constraint, to know a priori the statistical behavior of your data, right? In this case, there are plenty of techniques which we can effectively categorize as you can see here as general purpose, as those that exploit the data correlation, as these are sent down the channel. They can be time-based. They are trying to predict the value that you want to send. They are coupling-based, etc., etc. So let's go ahead in the next few, let's say 10 minutes or so, to mention some of those so that we get the basics of all these encoding schemes that have been developed over time. And in the meantime, you will see which elements of these techniques have actually inspired us to come up with our novel techniques, which, as you will see, are more efficient from several of those that have been developed in the past. So I'll begin with the general purpose methods that have been developed, and the most famous one from Richard Stein and Wayne Barlison is, of course, the bus invert technique, which is a technique that later on was also adopted, in commercial products like DDR memories and so on and so on. So the fundamental idea of this method is extremely simple, right? You want to send the data that we have at the left-hand side, right? And we basically observe the word that we're about to send. We perform XOR operation. If we observe that we have transitions on more than half of the bits of the line, then we send the inverted version of the word. For example, we had after the all zeros 1 0 1 1. We don't send this because this will cause 3 transitions. We instead transmit 0 1 0 0, and that will cause only 1 transmission. And when you do that, you need an additional line that you see in green at the very right, which tells me whether the word that was just transmitted is inverted or not. So that's a very simple technique that works quite well in several benchmarks, as we will see later on, but not in all of them. So let's keep that inverting the words is a means to reduce transitions over your bus. And of course, this method has been evolved over time. And I present a later technique where you observe basically a window of n words, where n can be 16, 32, you name it. And then you select the bus lines where you have a 64-bit bus, let's say, and you observe the lines with the highest probabilities to switch, and you add them to a mask. You see you have a mask computation here, and you apply bus inversion exclusively on these lines, and you do that in order to reduce the transitions in the very, let's say, busy lines, but at the same time to avoid increasing the hardware of your encoder. This is a point I didn't mention earlier, but I think I should do it now. When you develop any technique that has to do with encoding, there are 2 things that you need to pay attention to. The first item is how good your scheme is in terms of how strongly can it reduce the transitions and still carry the information. The other important item is how much hardware and how much power you need to perform this encoding, right? Otherwise, if your encoder is too complex, basically it counterweighs all the power savings and you end up with a zero-sum equation. If in some cases you may even start losing power, right? So you need to be aware of that as well. And not all of the techniques pay attention to that component, as you will see later on. So moving forward, another method which is called adaptive bus encoding, you see here M lines effectively, and what you do is you take each of these lines, you select it as a basis, and for example, I have here with all the process, which line is your basis line, and you see that with the green word, additional word that you see at the bottom of the slide, and at the very right, you see another green column, or a column in green, which tells you. So here, for this specific encoding scheme, you need to send additional words. Therefore, you have a drop on your overall bandwidth, and you need some redundant bits, as we also saw in another techniques, in order to transmit the information that the decoder will use to retrieve the original data, right? So all these are the components that you need to consider when you develop a new encoding scheme. So So some more elaborate techniques, bit shifting, you attempt to perform some, to shift bits around so that you end up with fewer transitions as you transmit your data over the channel. And you can have all kinds of operations, inverts, as you can see here, right shift, left shifts, or you leave the data as they are because they do not produce many transitions in the first place, and so on. Another method that you can use is basically you can try to take a couple of words, as is done in this technique that you can see here, and you reorder them so that you end up with fewer transitions. And this is an idea that we have actually used in the methods we have developed, but in a much broader sense. The drawback of this specific method is that they do not report on how they did it and what's the cost of the circuit in terms of power, which, as I said, is important. Otherwise, you cannot evaluate what are the actual savings, right? So moving forward, there are other adaptive schemes that basically attempt to exploit the data correlation as you transmit your data, at the same time to observe how much the data are correlated with each other. And if you do that, instead of transmitting the data itself, for example, you can just transmit a one hot encoding word, right? So one bit basically will switch. And once you receive this one hot encoded word, then you can look it up in a dictionary and say, oh, this is the piece of data that I was meant to send on the bus, but I didn't because I wanted to save power. And I sent a word that had only one bit switching, right? So frequent value and adaptive dictionary are some methods that utilize this kind of encoding. Of course, you can see here that you start requiring quite some hardware because you need to employ these buffers or memories, or which basically serve the purpose of the dictionary. And this method here, the hierarchical value encoding, is a similar method where you go and you do more elaborate observation of smaller chunks of data across your bus, and you observe the correlation, and you send or you don't send the data because the decoder can guess which data you intended to send, and basically use those, and you save transitions over the bus. So all of this, but again, you need to be careful not to increase the complexity of your encoder and decoder. Another category, be briefer and briefer as I move forward on these techniques, is the ones that translate, if you like, or transform the word, the data word, into right? So if you here, you have a piece of data and you translate that into some delay. So after some time, you actually receive the data, and depending on how late or how early you received a transition, you can tell what is this data. The biggest drawback of these approaches is that because the value of the data is transformed to a delay, basically, excuse me, the bandwidth of your communication goes down. The slides keep jumping, I don't know why. Anyhow, so we have some of this in our techniques that you will see later on, but not exactly that. We do something smarter to overcome this drop in bandwidth as you see here. So another category is to try to predict coming up the value of data that's up there for every specific bit, right, as you can see here, or basically for the full word. So you can try to predict the bit on a specific line, and if it's correct, then fine. If not, then you need to transmit the data, right? So Ricardo, I don't know why the slides keep jumping, but don't think I can do much. So, bit prediction helps you basically try to guess each individual bit on the bus. And if you guess it right, then you don't need to transmit anything. The information is already, let's say, in the decoder, and you save transitions. You can try to apply such a method across the entire bus, right? So let's say my value was FF on an 8-bit bus, and I'm guessing based on the data I've seen so far that FF is the next word as well. So you don't need to perform any basically transmission. I have this already, and if my prediction is correct, fine. If not, then you need to spend a little bit more of energy to transmit the new piece of data. Now, these last two couple of methods, basically, the coupling-based and the interfaces with asymmetric termination, they are specific, I would say, to the underlying technology of the specific channel, right? So the ones that we have discussed so far, they clearly and they only manipulate the data without considering so much the characteristics of the channel, right? So here, in the next ones, the ones that go to address the increase in the coupling capacitance, basically, instead of trying to reduce the number of transitions with respect, let's say, to the ground, 0 to 1 for each individual lines, they also observe what happens to the adjacent lines, because this coupling capacitance, as you can see here, the CI, tends to be higher as the dimensions of the chip of the interconnects basically shrink effectively as you move into more advanced technology nodes. However, if we talk about interchip interconnects, meaning interposers and so on, which is the one we have focused, these are not really relevant because there you have the luxury to place the wires relatively far from each other within, of course, reasonable distance, right? And you can easily, with same spacing, just get rid of high coupling capacitance. So effectively, the capacitance that we care about is the traditional interconnect wire to ground capacitance, the CL that you see here. So moving forward, there is another class of methods that deal with buses that have an asymmetric termination, and this is something that typically happens in DRAM interfaces. So as you can see, the simple circuit here, you have a driver, right? You can drive your bus lane into high 1 or low 0, and you have a pull-up resistor, as you can see here, which is actually helps if you want to drive your bit line to 1, but it works against you if you want to drive it to 0, because you have a continuous path from VDD to ground, and you always basically consume power. So in these types of method, in types of channels, you should not aim to reduce the number of transitions. You don't care so much about this. Instead, you rather care to reduce, for example, the number of zeros, right? So all of these techniques that I have basically discussed have more or less focused on these two elements. Now, the last one, the ones for asymmetric termination interfaces, are already applied in memory interface, as we see, and the famous one is the data bus inversion, which is used not only actually to lower the energy, but more importantly, to reduce the power supply noise when you have your memory interface, all bit switching, and so on and so on. So this is a method that you will find in many DDR methods, and I would recommend you to also read a recent issue from the Solid State Circuits magazine that discusses this, the use of this method in modern DRAMs. So we have talked a lot about a lot of techniques relating to how to reduce transitions on parallel buses, on parallel interfaces. But as you know, you don't always have the option to use a parallel interface because you don't have, so many pins that you can use and so on and so on, especially when we talk about technologies 2.5D, where you have interposers and you may have several chiplets and you start running fast out of routes to route power, ground, and signals as well. So in that case, and as you know, serial interfaces, as we know them, are widely used. And there you can basically categorize them as SERDES that are source synchronous. Again, it means that you make the clock signal available to the receiver, so you don't need to care about recovering the clock signal. And on the other hand, the source asynchronous, which basically puts more constraint in your encoding method. Remember, what we were trying to do primarily so far was to reduce the number of transitions, the number of switches between zeros and ones. But if you do that in a source asynchronous SERDA circuit, then it's extremely difficult to extract, to recover the clock, because the transitions, right, these edges are actually used from the clock data recovery circuits to recover the clock and synchronize the data. So there is a trade-off, let's say, about how much you can reduce the number of transitions without losing your synchronization for the received data. So if we talk about encoding in source synchronous serial communication, you see a couple of techniques that I have put here. You basically XOR successive data words. You look if your data are correlated, or you invert the event bits of the words, and this can lead to fewer transitions and so on. And you don't need to care whether you have any transitions at all, or you have many transitions. All you care about is how to reduce the power, right? You don't care how many edges are observed across the data stream. The situation, as I said, is different when you go into source asynchronous, and you need this block here, as which is shown as CDR, the clock data recovery, in order to recover the clock and then capture the data and do the serial to parallel transformation and receive the original word. So in that case, you can just blindly go ahead and try, let's say, to flatten your signal, right? You need to have some transitions in there. And you also need, in principle, to perform encoding so that the DC balance, in other words, the number of zeros and ones that is observed across your data stream, remains roughly equal. And I'll show you some results on this later on. These are some, let's say, prerequisites for several services. So some schemes that have been developed in the past, as you can see here, have 8 bytes to 10 bytes transformation, right? So 8 bits to 10 bits. So you get basically a character of 8 bits and you transform you 10 bits, you add 2 more bits, and that can give you some more transition. This is redundant bits, but of course, this comes at a cost of 20% of bandwidth, right? You had 8 and now you had 10 bits. And of course, there are some more later methods, more sophisticated, where you go from 64 bits to 68 and 128 to 130. And as you can see down here, the overhead on the bandwidth is even lower. Now, a method that also used is basically to scramble the data. So the original data stream goes through a circuit which consists of several XOR gates and so on, and performs scrambling and adds a lot of transition. And here you don't increase the overall number of bits or symbols, if you like, that you propagate. So no bandwidth overhead, but you add a lot of transition. So typically your power will go up. So it has more transition than the original bit stream that you intended to propagate. So that's all I had to say in terms of introducing, let's say, the field. In the next few slides, I'll discuss the methods that we have developed in my group and we recently published. So I'll start with the adaptive word reordering, which is a method that applies to parallel buses, and I would say applies to wide and slow buses. So the idea is the following. So assume, as you can see at the left, we have a column of bytes, right, that we tend to propagate, and we split that into groups of n words, where n equals to 4 in this specific case, and then we perform reordering of these words within each group, and we basically find the ordering of the words that leads to fewer transitions. And if you do that, you can end up as you can see in this specific example, from 46 transitions down to 32. That's 30%, okay? That's a significant number. Remember, I'm talking about reducing the transitions. I'm not talking how you're gonna do that in hardware just yet, right? So when we try to approach this problem, okay, that looks a promising idea. Let's see how we can implement that in hardware so that we don't need to spend too much power to do the encoding. So this problem can be approached as the well-known traveling salesman problem and can be solved optimally. But if literally, if you try to implement that in hardware with circuits, just forget about it. It's not going to happen, right? It's not going to work. So we started to rely on another algorithm, which is a nearest neighbor algorithm. And I had some animation here, but I can't use it right now. I'll explain with words how it works. So we start from the very, very left that we have the word 0001111, and then we determine the cost of the neighboring words, and between 1, 6, 3, and 2, we select the one that has the lower cost. So 1, you see basically the edges with the orange color, and then 3, every time we select the next node, which is the next word with the lowest cost, right? And so on, and we end up with a sequence that most of the times will produce the lowest or near lowest cost in terms of a number of transitions. So that's a better, let's say, a less complex algorithm to implement in hardware, but you still need to determine the Hamming distance among the different words that are candidates to be sent along the bus. So how do you do that in an efficient way, right? So we'll do that in a second. Before we do that, let's see how much, theoretically at least, you can save by applying this nearest neighbor algorithm in different benchmarks. So what you see on this table, we have a list of different benchmarks that are available to us through the EuroExa and the ExaNode projects. These are European Horizon 2020 projects. And as you can see, this is our techniques where we had a block of 32 words to reorder, or 64, and we compared with some of the techniques I discussed earlier on, the bus invert, the adaptive partial bus invert, and so on. As you can see, we are clearly the winner and by far in terms of reducing the number of transitions, except when it comes to totally random data, where we are comparable with this technique. Now, remember, the bus invert technique may not perform here very well, but it has the simplest hardware. So our goal was not only to demonstrate that we reduce the transitions over the bus, but we do that in terms of hardware very efficiently. And I'll try to convince you that we have done this as well. So in order to reduce the number of transitions on the bus, and for this specific method to select which is the next word you intend to transmit, you need to determine the Hamming distance, right? And if you try to do that with XOR gates and other trees that add all the ones that are produced by the XOR gates, forget about it, right? It's totally inefficient. So what we did was to model or represent, if you like, the Hamming distance between two successive words, two candidate words that are to be sent with a delay, right? And how did you do that? We effectively use this circuit, right, where you have some inverters, like a delay, classic delay line, that you insert some additional transistors, right? We took the original idea from this paper, and then we drive it with some of these transistors with the result of the XOR operation of successive words. And these delay lines, okay, we have one for each pair of lines, will lead to a different delay for different pairs of words, right? Depending on their Hamming distance. So if you do that, you end up with a circuit like this, which we published back in 2019 at the DATE conference. And each pair of words feeds each line, produce a different delay for each of these delay lines here, and the ones that arrives the earliest to these latches that you see at the middle of this circuit is the one that has the lowest Hamming distance, and this is the one that should be transmitted next. So with this circuit, if you apply it, it works like this. So the animation here is not able to be shown, so it does not help too much. But in this specific example, you have n words. As you can see, the one that arrives first is the purple curve, the purple pulse of word 1. So this is latch first, and the green pulse indicates that this is the word that should be transmitted. So the next word that you should see down the bus is word 1. Now, of course, if you do that, right, you need also to add some bit lines to your original bus in order to transfer the index of the word among the n words that you're about to send down the bus. So if you had 64 or the 32 bits, then you need another 5 additional bit lines to provide the index between 0 to 31 and so on, right? So you need to include that, but the decoder circuit literally is relatively simple. You just look at the index of the word you just received and you put it in place in the received buffer, right? So we went ahead to simulate that, as I'll show you some results. And this is basically the block diagram that you can see at the bottom of this slide is a setup that we have used. I have some animation here, and that's why this has been flattened. You cannot see some information, but doesn't matter. Most of the info is there. So we implement that in the 65 nanometer technology, and we measured the power that was consumed for the different benchmarks. And this is the power spent for the encoding and decoding circuits, right? Not about, not the power that is consumed by transmitting the data. So this is the overhead, actually, of each of the encoding techniques, ours and the ones we compared against. And you can see that our method does not consume a lot of power. All the numbers are in milliwatts, right? The bus invert is indeed the simplest one, hence consumes the least power, but some other ones you can see that consume much more compared to ours, right? So as I said, in addition to power, you need to be aware of the effect that your encoding scheme will have on the latency of the system and the bandwidth as well. So our method does not have any bandwidth, any impact on bandwidth, because all the time we transmit some word, and the additional bits, the index of the word is transmitted in parallel as well. However, because you need to do this reordering of words, you need, in the worst case, to for example, the first word of the n words might be transmitted last one, right, as the nth word. And in that case, you have to suffer a latency of up to n clock cycles in order to put the words in order at the receiver. Now, if you consider applications like DMA, right, this should not be a problem. But again, this is a price you pay to save power for this specific technique. So what you see here on this graph is how much savings our technique produce, and this is real savings, meaning we have included the overhead of the encoding and decoding circuits and the savings you observe by reducing the transitions on the bus. So here we have different blocks of words that we reorder, 16, 32, and 64, and you can see that it changes significantly from 14 all the way to almost 24%, 23% for 1 millimeter length. And as you increase the bus length, because you can have longer lengths, you can only save more, right? The overhead of encoding does not change. The only thing is you save more power. So longer buses will lead to higher gains, to higher savings, as you can see here. And what's the effect of how the technique works on different bus widths? Well, you can see here again that you save between 18 to 20% depending on how wide your bus is. Now, the last few graphs about this technique. Here is a comparison with other techniques where we have also implemented all the encoding and decoding circuits. And you can see that if you add the overhead of the encodings, many of the existing techniques basically do not perform so well. So we do relatively good, as you can see here, with the purple and blue line, and we're not performing well only for extremely random data, as we have seen in a few slides earlier. So this is a chip we have implemented in TSMC 180 nanometer technology. We have prototyped this, and we are actually trying to get some measurements. All the results I show you so far were simulations to see whether we can actually get some gains out of these techniques, or real silicon measurements. So I'll spend the rest of my time basically to discuss how you can do smart encoding along the same lines in serial transceivers, basically. So again, the idea is to reduce the number of transitions, but be aware here, you cannot have what we call excessive run lengths. You can see here, you cannot have large numbers of consecutive ones and zeros, because you need to have some transitions to help the CDR circuits to recover the clock. So what we did here was basically to reorder again words. This is a single bit lane, right? You're gonna send all the data. So we want to reorder the words in order to achieve the lowest number of transitions. But if we have long sequences of ones and zeros, then intentionally using this S parameter that you can see here, we introduce transitions, right? And of course, depending on how big the step you take in order to introduce a transition is, you reduce the transitions more aggressively, right? So every 6 bits, you introduce a transition, then you are around 40% in terms of fewer transitions. If you move on to 26, then you take a bigger step and you can save more, right? So this is a design parameter that you can basically use in order to adjust how aggressively you reduce a transition across the bit stream. So this is a circuit. This is a slightly modified circuit from the previous one I saw you. I'm not going to discuss this nor the decoders circuit for the sake of time. I would like mostly to focus on some numbers which I think you'll find interesting. So here again, I list the overheads of the encoding and decoding circuits for different steps, where S is again the run length, the number of consecutive ones and zeros that we allow. And as you can see here, the numbers are not excessive, right? About 2 milliwatts of the encoder and less than 1 milliwatt for the decoder. But because we introduce some transitions that all of the techniques, most of the techniques do in SerDes, we have to get a drop in the bandwidth, which is not that excessive, is on the order of 5%. However, the latency is not affected, and the latency is not affected because typically on the services that we have looked, at least, you have a bit stream which is transmitted like a full packet, and at the end of the packet you have a CRC, right, to check for errors. So you need to receive the entire packet to perform CRC and then to say, okay, my data was received or was not received correctly. So since you need to wait for the entire packet, even if you reorder the words, there is no problem. As you receive it, you put them back in the right order and the latency is not affected. So latency is not an issue here. You just need to take a hit depending on how many transitions you introduce through the S parameter, and that will affect slightly your bandwidth. So again, we simulated this with a 65 nanometer technology, 250 megahertz of operation, and the numbers were quite nice here, right? So for the same benchmarks that I have shown to you before, and for either 16 or 32 words, the energy was reduction that we achieved was to 50%. Of course, if you, depending on the day, when we implemented this technique, we also wanted to guarantee that we don't end up with many errors, right? Because I said we need to introduce transitions in order to maintain synchronization. So we implemented this method, or actually let's say a crude version of this method, because you cannot implement your analog-like circuits on an FPGA. And we have these two FPGA boards, an electric link, as you can see here, the coaxial cable and the optical cable, through which we send down encoded data, and we observe basically if the bit error rate after encoded increased, right? And what I show you here are some maps, like smooth plots of the errors we observed as we applied different run lengths, meaning as we checked how many transitions we introduce into the bitstream, additional transitions, in order to maintain synchronization. Overall, the optical link was not performing that well, but the electrical cable for this specific setup could allow us really long run lengths without running into any errors. And I have some arithmetic, figures that tables that you can see more specific numbers if you cannot distinguish that from these graphs. The bottom line here is that the electrical cable seemed to be more robust on this specific setup rather than the optical cable, and our encoding didn't really suffer from synchronization errors as long as we selected carefully the S parameter, right? So, and that you can see here. So we have different values of S, right? And we have different benchmarks, and this is the electrical cable, and this is when we send the data scrabbled, which is with plenty of transitions, no power savings, and this is if you send them unencoded. So if you send them unencoded, because you may end up with long transitions of ones and zeros, you may get some, let's say, noticeable bit error rates, as you can see here, 10 to the minus fourth. However, in all other methods that we applied, you wouldn't observe any significant bit error rates, right? For the optical cable, you need to be more careful with your S parameter. If you allow longer run lengths, longer consecutive, longer sequence of ones and zeros, you may start observing some bit error rates on the order of 10 to the minus 5. If you keep the S low, as low as 5 bits, consecutive bits, you don't again observe any significant errors. And just to show you the eye diagrams, this is something that typically people want to see from this kind of simulations. This is what they look like. You can see that you can observe the eye opening is quite well. It's a bit more, let's say, narrower at the optical channel, distorted at the optical channel, but still is sufficient. So these are the last slide before moving into conclusions is to demonstrate that our methodology, even for if we exclude CMOS drivers, because all the simulations were done with CMOS drivers, there are other drivers that are used in SerDes schemes that are independent, let's say, of the number of transitions that occur over the bus. Even there, the measurements we did on this specific FPGA boards, we demonstrated that a proprietary PHY that we had at our disposal using a scrabbler was consuming more power, as you can see here, about 80 milliwatts compared to the method we propose, which can be as low as 68 milliwatts, which is on the order of this like 20% reduction, right? Even if you exclude all savings on the bus. So to wrap it up and to give the word back to you for any questions, I discussed several, I would say plenty of encoding methods that have been presented over the past. And the take-home messages are that you can actually reduce power significantly, but you need to proceed carefully looking always at the overheads, the power overheads that your encoding and decoding circuits will bring in. So they should not be very complex. And you also need to consider, right, the effect that your encoding scheme will have either on the latency or the bandwidth. So depending on the application, you may choose one technique over the other. So that's all that I had from my side. Thank you very much for your attention and for listening to this talk. And Ricardo, if there are any questions, I'll be happy to answer.
Thank you very much, Vasilis, for the nice talk. So I'm seeing a question here by Rodrigo Verdic. Thanks for the talks. Do you see any application of adaptive bus encoding for interfacing neural networks while preserving his behavior, using weights or something to keep the correlation?
Right. So I can answer this in two ways. So it's an interesting question. It's a dimension I haven't an angle I haven't thought so far. So Rodrigo, thank you very much for this question. So if you think of how you can reduce the power spent for transferring all the weights and all the parameters for a neural network from the DRAM to the MAC unit, right? Then I can see some scope there because I know it's a very expensive operation. But remember, this is if it is a DRAM interface, there, remember I mentioned a couple of techniques. You don't care so much about the transitions, but you care about the number of zeros and ones depending on what is the termination scheme that you use on the DRAM interface. You want to reduce those. So because a DRAM read for in the context of neural networks is a very expensive operation, I can see scope there for this kind of schemes. And actually, we're trying to develop a method that is dedicated to DRAM interfaces. All right. Hopefully, I'll have some results to show maybe in the next talk. Now, if you imply to use, let's say, neural network or machine learning to adapt the data that you send over the bus in order to reduce the transition, if that's what you imply, then it's something I haven't thought. So I don't have a clear answer. I don't think I have any intuition on this question as well that I can offer you right now. But maybe it's something that can be explored, right? I think the trick there will be you need a large number of data in order to, train your network to tell you what's the right encoding or scheme to be applied to that specific data set.
Okay, thank you. I have a small question. Do you have observed what if there is a change in the power reduction depending on which technology you are using? If it's different or the percentage is similar?
Right. Very, very good question. So there are several, components to this answer. So I talked a lot about the dynamic power, right, that we care about. But at the same time, leakage is important, especially in advanced nodes and so on and so on. So the specific circuits I've discussed, they are, I would say, analog-like circuits. So as we move into, smaller nodes, I would expect the encoding circuits to improve. So the overhead, in my opinion, will most likely will reduce a bit, but not so much because the delay lines are analog circuits. So you need to size them carefully in order to achieve the representation of Hamming weights into latency, into delays, right? And maybe you don't have too much headroom to improve the overhead of the encoder. So I would see some change on the order of 5 to 10% reduction, in the power consumed by the encoder, but not much much more. Now, the channel, because typically we develop these methods for interposers, interposers do not really, or they're not expected to scale too much. So you will have 65 nanometers or even maybe above, right? So if anything, the data, the power used for transmitting the data will not change dramatically, because it's not the power on the chip, but it's the power consumed on the interposer between the chips. That's my my feeling on that. Right.
Thank you. There is a comment about his questions by Rodrigo.
Yes, thanks, Rodrigo. Okay, thank you for clarifying that. Yes, as I foresaid, I have a student who works that, and we have seen some interesting observations, because effectively, DRAM chips are 8 bits wide, the buses, so, and then they basically put them all together and send them out. So we're looking into that problem. I'm hopefully I'll have some results to present very soon.
Okay, thank you very much. I'm seeing no more questions here in the chat channel.
All right.
So then I would like to thank you again, Vasilis, for giving us this very nice talk today.